This video is part one of network basics, where I'm going to go through just some of the fundamentals that I think that's very important to know and understand when dealing with the topic of networks. First thing to note is if someone was to ask me, well, what's a network, or what does a network mean to me? I just think of it's really just a collection of objects that are related in some way. An example of that would be my family, my social network, for example. I could think of a traffic network that links cities together, for example. Okay, so just thinking of examples of networks, I think is a very good way to start. Okay, let's go through some quick terminology. Okay, so when in the topic of networks in mathematics, though, I think there's quite a bit of terminology that you need to know, and I think that's probably one of the reasons why students, I guess, initially do find this topic a little bit daunting. But in reality, we live and breathe networks on an hourly basis. It's part of our life, in fact. Just the way we interact with others and how we view our relationship with others is in itself a network. So I think, just appreciating that fact alone, I think will really drive home the point that this topic is a very important one, and it's great to articulate these kind of real life situations and really sort of study them in more detail. So let's look at this diagram. These dots, we call these dots vertices. Okay, so I'm just going to write. Okay, so these are vertices or vertex, for example, if it's singular. Okay, so there's a collection of vertices here, and we usually label them. It's not the only way, but we usually label them with a capital letter. Sometimes it could be lowercase, but so we have vertex A, vertex B, C, D, and E. Now, these represent the objects. So they could be towns, for example. They could be people. They could be, for example, transmission stations for power, or they could be pumping stations for water. I mean, it could be anything. So these lines that join the vertices, these are called edges. Okay. Again, there are other names, that we can call them, but we're just going to focus on probably the more common terminology. Okay, so vertices are linked with edges. Okay, notice here a vertex D. It seems to be like a road that leads back to itself. So it's almost like this could be town D, and sort of traveling along this edge, and you sort of come back to where you started. This is called a loop. Okay. Now, notice also from vertex A to vertex C, and vice versa, it's actually two directional or bi-directional. Sort of, there's no direction indicated here. Notice that there's two ways to go from A to C directly. So we've got this path here, and we've also got this path here, or this edge here. These two edges, they could be two different roads, but linking the same two towns. These are what we call multiple edges. Okay, that term's a very important one. Okay, so because later on in the topic there's a requirement that we cannot have multiple edges between any two vertices. So I think it's good to know that whenever you see this situation, it's good to sort of put your finger on it and say, that's a multiple edge. Okay, next thing we're going to talk about is the degree of a vertex. Okay, so let's have a look at, say, for example, vertex C. So I'll use a different color here. Vertex C, the degree of a vertex talks about how many connections basically lead to it. So if you take vertex C, we have 1, 2, 3, 4. Okay, 4 connections, so leading in and out of it. So this one is degree 4. Okay, vertex E. What would be the degree of vertex E? So again, how many lines or edges are leading to E? Okay, or away from E? This one is degree 1. Okay, and so on. A is degree 3. Okay, B is degree 3, and D would also be degree 3, because if you were to basically ignore the loop for a moment and just look at if I was to draw a circle around D, this is a good way to I guess, to count the degree or to determine the degree of a vertex. If you were to draw a circle around the vertex, how many edges are cut? 1, 2, 3 edges. So this this vertex D, this would be degree 3. Okay, and B is also degree 3. Okay, A is also degree 3. So quite a few degree 3s there. Okay. Now a very interesting observation here. Count the total degrees, or the total the sum of all the degrees. So 1 plus 4 is 5. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. How many edges do we have? We've got 1, 2, 3, 4, 5, 6, 7. The loop is 1 edge. Okay. The degree, or the sum of the degrees in a network, is double the number of edges. Okay. Very, very important, that one. And that's a very useful rule, that one. It's actually called the handshaking lemma. We don't need to know that particular term, but it's almost like if you're shaking hands with somebody, there's 2 people involved, but there's a single handshake. So just something there just to sort of keep in mind. Okay. So let's move on then, and I'm going to use a different board now. Okay, so we've talked about the degree of a vertex. Okay, actually no, before I do that, one other thing I'd like to, actually I'll use this diagram one more time. We talk about the concept of a walk, a path, and a closed path. So again, sorry, I'm just going to use a different color pen here. Okay, so we have a walks, okay, paths, okay, and we have closed paths. Okay, closed paths are called cycles. Okay, we'll see why. When you talk about a walk, okay, a walk is basically any journey from one vertex to another. Okay, probably you can define it to be whatever you like. So a walk could be, for example, A to B to C to E, back to C, back to B to D, around the loop, back to B, back. I mean, a walk could be whatever you like. Okay, any journey from any one vertex to any other vertex, even back to itself. Okay, so a walk, there's no rules attached to how you travel around this network. A path, however, does impose a limitation. So a path is any walk that has no edges repeated and no vertices repeated, in fact. In fact, by not repeating the vertices, you're not repeating the edges anyway. So an example of a path would be, for example, A, B, D. So I might just put the examples here. Right. A, B, D. A, B, D, no vertices are repeated, and obviously no edges are repeated either. Okay. What's another example of a path? Can you identify another example? What about E, C, B, D? Okay. BAC. Okay. BACB though, or is something that is a little bit different. Now, yes, we've only used the edges once, but we have repeated the start and end vertex. That's called a closed path. Okay, so this term here, a closed path is a path that starts and ends with the same vertex. Okay, a regular path, notice, for example, e.g. ABD, the start and end vertices are different. So starting at A, ending with D. A closed path, however, is starting and ending at the same vertex with no edges or other vertices repeated. So using this diagram, okay, we can see that there's a cycle BAC. BAC, but then back to B. Okay, so starting at B, going through AC, so there's our path, but then to close the path, we have to go back to B. That's why it's called a closed path. It's closed up. It's like a shape that you can color in, and you can sort of fill it with color, or sort of forms a shape that you can sort of fill it with something if it was a container. If it was open, well then it can't be filled. So now I'm ready to use another board, of course. So, and I'm just going to continue on with our just our terminology. Okay, so we have two other or three other concepts that I want to go through before I finish the video on part one. And first of all, this is the concept of what we call a connected network. So far, all this is just terminology. So an example of a connected network, okay, would be, and I'm just drawing, this is all just random, sort of random vertices. Okay, so there's an example of a connected network. A connected network means pick any two vertices. Is there a way to get from that vertex to the to those two, between the vertex you pick, the first vertex, to the second vertex? In other words, if I picked vertex A and vertex C, is there a way to go from A to C? Yes, of course there is. That's not always the case though. Okay, so this is what we call a connected network versus a non-connected network or unconnected. Okay, and an example would be, and I might, okay, so for example, I might actually draw a very similar network to the first diagram. So, and I might just do that, and okay, there's our closed path, there's our cycle there. And I'm going to join A to E, but something happened. ED, I mean, there could have been a road closure or something. This is a non-connected network. In other words, if I chose the same two vertices, A and C, is there a way to get from A to C? And you can clearly see here, there's no way we can get from A to C. So this is really two sub-networks, okay, or two smaller networks that form obviously a larger network, but it's sort of in two pieces, the two unconnected pieces. So this is the concept of a connected network, and that's actually very important in further applications of networks where we have to assume or we have to deal with networks that are connected, and if they're not connected, that can complicate things obviously, and certain things just won't work unless they're connected. Okay, then we talk about the concept of a directed network. Okay, so far everything that we've looked at, we've assumed that you can travel in two directions. So in other words, we could travel either from A to E or from E to A, okay, or from E to D, for example, or from D to E. There's no direction stated. We could talk about a directed network, okay, and a directed network is exactly that. They're like one-way streets. So I might just use the same diagram, or very similar diagram to what I've done in the previous examples. Okay, and there's B, and this time round, I'm going to put arrows. All right. So, okay. So this is an example of what we call a directed network. In other words, the flow is indicated by the arrow. Okay, we can go from A to E, but we can't go from E to A. All right. We can go from E to D, but can't go from D to E. That's not allowed. We can go from D to C, fine. C to B, fine. B to D, fine. So that's fine. And that's a directed network. So that's where the arrows show the direction. Okay. We also have the idea though, and we haven't spoken about this yet until now, where if these were roads, is there something to indicate how many lanes the road is? I mean, are they two-lane roads, three-lane roads? Are they major highways? So we have this idea of what we call a weighted network. Okay, and okay, might draw our favorite little network diagram. Okay, and that's A, B, D, C, and there's B. Okay, I didn't put arrows on it, so it's not a directed network, but I could put numbers on the edges to indicate either a cost, or could indicate the flow, or how big the edge is, how much capacity it could carry. So these numbers could mean anything. Okay, so sometimes that could be a cost. For example, if I'm building a road network, or I'm building an electricity network, this could be the cost. For example, could cost me $3 million to build a set of transmission lines from A to E, $5 million from E to D, and so on. Okay, so this comes in very handy when there's multiple ways of getting from one vertex to another, and we have to minimize the cost. Okay, because that's one of the applications of networks is cost minimization. Can we combine directed networks and weighted networks? Of course we can. Does that mean that because the arrows are there, we can't have numbers there? Oh, you can have numbers there as well. So if I was to draw a directed weighted network, okay, sorry, I'll just put that there so you can see that. Alright, just bear with me. Sorry, I'll just get that focused again. Yep. Alright. So again, I'm just drawing a. Alright. Yeah, I could have arrows. Okay. And I could have weights as well. So 3, 5, this could be 8. I'm just coming up with some random numbers. Okay, so this is a weighted directed network, or a directed weighted network. Doesn't really matter, so I'll just use weighted first. Okay, so this is a weighted directed network. Okay, so hopefully the terminology, and you're welcome to go through the video a few times, and sometimes it can take a few goes to kind of get used to the terminology. Okay, so a quick recap. All right, just quickly going back to this board here. Okay, the first and most important thing, what is a network? Bunch of objects and their relationships, okay, and the relationship between them. The objects are called vertices, okay? The connection or the relationship between those objects, okay, is called an edge. Okay, so that's really networks 101, all right? Then we start to get into a bit more detail. Loops, multiple edges, degrees, okay? How many connections, or how many connections go in and out of a vertex. We talk about the relationship between the degree, or the degree of a network, okay, and the number of edges in that network, or the sum of the degrees. We saw that the sum of the degrees double the number of edges. We talk about the idea of walks, paths, and, sorry, I'll just write that again, closed paths, which are called cycles, okay? So, okay, then we just spoke about connected networks, non-connected networks, directed networks, weighted networks, and weighted directed networks.